So we talk about differential amplifiers. Differential amplifier is just two transistors basically competing with each other. Like we apply a signal and one of them takes the positive half and the other one takes the negative half, right? The purpose is to amplify our AC signal, but to degrade our common mode signal. And this amplifier is actually placed inside the op-amp, right? So the V1 goes through here, gets connected to minus sides, and V2 connected to the plus sides. And then you learn the op-amps. Basically, this one has a gain, and that gain is used to create this inverting amplifier or the differential amplifier. So let's look at how the differential amplifier works. We have two signals, and we can divide these two signals into the differential and common mode signals, right? Let's say one of the signals is 5, and then the other signal is 1, right? V in 1 is 5, V in 2 is 1. Well, we shall write this as 3 plus 2, and this one we shall write as 3 minus. And this shows the common signal, and this part shows the differential signal, right? And what this amplifier does, looks at these signals as common and differential. And the 3, the common signal, it doesn't get amplified, but plus 2 minus 2, it gets amplified, which means you get to see the output signal, right? So that's the logic of differential amplifiers. This can be 5-1, or this can be 5 cos omega t and 1 cos omega t. Same logic. Basically, the common and differential signal logic doesn't change. And you again do the same thing. First, you have to solve the DC. What is the DC current and what is the voltage on the, in this case, CE or BE, right? You have to solve DC of the amplifier. And after you find the DC currents, you get to find small signal parameters. What are the small signal parameters for a BJT? R pi, GM,
RO.
RO, yeah, exactly. R pi, GM, RO. And you already know how to find these ones. And then you find the AC small signal model. You draw it. But this time for the AC small signal model, we have a differential one and we have a common mode. So when you do the differential mode and the common mode, we use half circuit. You use the half circuit approach. And we look at each case, the differential and the common mode case separately. So first, let's look at the differential mode case at the left. What you do is you do the superposition, right? This was, I assumed 5. I assumed this was 1. So that means this is 3 plus 2. And this is 3 minus 2. So doing superposition means, well, I'm not looking at this and I'm not looking at this, but right now I am only looking at 2 and minus, like differential, right? So basically VID over 2 and minus VID over 2. And then in such case, in this case, what is VID? This is VID over 2. This is minus VID over 2, right? This is 2. What is VID? It's 4, right? 4 over 2 minus 4 over 2. 2 minus 2. We are looking at differentially. So this differential signal, half circuit of it, basically half circuit of the differential mode, gives you a simple tool to solve the circuit. What you do is you divide the circuit into half. What you do is you divide this circuit from here, and every single point touching here is ground. And then you draw one of the half. That's called half circuit. So when you do that, it becomes easier to solve the circuit. So you solve the circuit. And when you do that, we find this. This is VID over 2. That means V pi is VID over 2. That means this current is GM times VID over 2, but minus takes the current this way. Then you multiply this with RC. I assume R0 is infinity. This is your output. Then this is your output, this is your input. Output over input, you basically cancel those, and GMRC becomes your gain. Are we clear here?
Evet hocam.
So this is also gain of a common emitter amplifier, right? So if you have a currents that provides you the same GM, you get the same gain. So what is the point of using differential amplifiers is your question, because now here you'll have 2 times of the currents DC wise. 1 current here, 1 current here, you are getting 2 times of the currents. But differential amplifiers enables you to get rid of the common mode signal, right? So that's the advantage. Now let's look at the common mode signal. And remember, we were using 5 and 1 as our input signals. And our common mode signals were, this time, it was 5, 1. So our common signals will be 3. I'm not using 2 and -2 because they were differential signal. I'm doing superposition, right? So this time I am shorting them and I'm applying 3 and 3. And the common mode tells you when you do this again, this line will be open circuit. And you redraw this ROB this time as 2 ROB because we have to make this circuit symmetrical, 2 ROB and 2 ROB. So you cancel this, right? Basically, you rewrote that as 2 ROB, 2 ROB in parallel. And then when you cut the line, everything that touches this line is open circuits. So if there was let's say a resistor here, it would be open circuits. You wouldn't be using it, right? If there was a resistor somewhere else, like here at the output, then again, similar. So the middle is open circuit. So what you do this time is solving the gain of this circuit, okay? And this is also a common emitter amplifier, but now there is a emitter degeneration. And you should be able to find the gain of the circuits from 301. And if you don't know how to do it, does it here for you. And you can check this one. And the gain of the circuit is GMRC divided by 1 plus GM1 to ROB. So in the differential case, it was only GMRC, right? But in the common mode case, now we have this gain, which means the higher your ROB, the less is your common mode gain. Okay? So we found the differential gain and we found the common mode gain. Now what we do is, now what we look at is common mode rejection ratio. Common mode rejection ratio is differential gain divided by common mode gain. And as you can see, differential gain divided by common mode gain gives you common mode rejection ratio, okay? So, having this common mode ratio as big as possible is our preference, right? Because we want to amplify the differential signal. We want to make this as high as possible, and we want to make this as low as possible. And the only independent term, change these terms independently basically, is this, right? So we should make this as high as possible, and also we should make these terms as high as possible. This will make that high. This will also make the common mode get high, but we will decrease the common mode gain using ROB high, right? And what is the way to make ROB high? If you look at the original circuits in the first circuit back in the first slides, this is the ROB model of current source, right? Because an ideal current source will have an infinite resistance. So this way is showing that the current source is not ideal, right? So basically we can think it like a non-ideal current source, obviously. Circuit was a current source getting an ideal current from somewhere else. And this circuit was that mirroring that current, right? This was actually how we did it in the class.
Şimdi bahsetmediniz diye oyunladım.
Yeah, so that's how we do it in the real microelectronics. So the chips inside your phone, they do it this way. So it mirrors this current, comes to here. The beta is big. If it is not big, it's not a perfect current source, right? Because now in this case, this is how it is. And in this case, there will be some currents because of the beta currents of these ones. So the currents here will not be perfectly equal to this, right? Because there will be these two currents summing up. So, and in that case, what happens is not a perfect current mirror, because this current, the one going into the collector, now will not be equal to this one, will not be equal to this one. But if beta is infinite, these currents are zero. That means this current is zero. That means this one and this one will be equal to each other. And then if the IS of this 1 and the IS of this is 2, basically it will be a times 2 current source, right? This is, let's say, I reference. Then we will be able to get 2 I reference. That is current measure. And this ROB is basically what you see here as the output resistance. And to make it higher, what we do is Actually, we add another BJT here, right? And we make it cascade. This way, you can increase your ROB. But what is the disadvantage? We want this VCE to be 0.2, right? We want this device to be in linear mode, actually. If you remember the BJT characteristic, this is VCE, this is IC. Characteristic was something like this. Here is what? 0.2 volts. So this is a fixed voltage, 1 volt, I assumed, because the current is constant. So this is VC and this is VCE. So this is 0.8. It should be smaller than 0.8 so that this transistor is in this region. This is, I think, called linear region. In the MOS, it's opposite, it's saturation. We want the transistor to be linear. That means we want this voltage to be smaller than 0.8. If I add another transistor here in the middle, now we have 3 transistors and all of them should have what? This voltage should be what? More than. To make this transistors work in the linear region, all of transistors should have a voltage bigger than 0.2. So I added one more. I basically increased this resistor, right? Because it's cascade now, but now it's 0.2, 0.2, 0.4, right? So if I add another one, it's 0.6. If I add another one, it's 0.8. This transistor will not work anymore, right? So adding a transistor basically takes this voltage higher, and that is called headroom. We don't necessarily eat from the headroom of our signal, because what happens is when we apply a small signal here and there will be a swing around this 1 volt, what will happen is around 1 volt we'll have a AC signal because it's amplified, right? So when we look at here, if we draw it, I assumed my DC is 1 volt here and I assume my AC is also 1 volt, which is 1 volt here minus 1 volt here, right? So when I reach this point, will this transistor work? 1 volt is my DC here at the output. And I applied a signal 0.1 volts here. And the gain of this circuit is 10, right? Then 0.1 times 10, I get a 1 volt swing, right? 1 volt down, 1 volt up. So that means the output will reach 0 and 2 volts max, right? 0, 2 volts. So when it is at 2 volt, the output, will there be current through here? This is 2 volt, this is 2 volt, there will not be any current. So that's why what I'm saying to you is the DC is important for a circuit to work fine. So this 1 volt should be picked wisely. That means this current should be picked wisely. Right? You see my point? So that's why when we add a transistor, we are increasing this voltage DC-wise, which means we are also increasing this voltage DC-wise to make this transistor work. But when we increase this voltage, we cannot host AC signal if it is big. It takes this transistor into cutoff because the current will be 0. So that basically adding one other transistor benefit is increasing the R-out resistance, this one, ROB, but the disadvantage is the headroom. So going back to the original discussion is today we looked at the circuit, we looked at it differentially, we looked at its common mode, we found the gains, and then having found the gains, we found the common mode rejection ratio. And knowing the gains, you can find the output 1 and output 2 as well, right? Because output 1, common mode gain times common mode input plus differential mode gain times differential mode input. Same with the V out 2. Common mode gain times common mode signal plus differential gain times differential input, which is minus VID over 2. And here your input is VID over 2.